Hello guys, this is the first video I'm talking about myself, so obviously I'm so excited, so let's dive right in. So today we're going to be talking about invariance and monovariants. These concepts are pretty much overrated, but these are too simple, even though its usage is a lot. Okay, so let's start. So first of all, what is an invariant? Invariant is a quantity or property that does not change under any allowed operations of a process. You're just looking for what doesn't change. That's it, simple. So identify what changes. First of all, you have to identify what changes. Then only you can think about invariance. And when you're trying to identify what changes, you might actually find what's fixed so that you can draw the conclusions. So first of all, we have something called the parity invariants. These are the most basic and easiest invariants ever. Simple. Even plus even is even. Odd plus odd is even. Even plus odd is odd. And odd into odd is odd. And even into anything is even. So these are pretty easy to do. Also, the key inside. If an operation changes a quantity by plus or minus 1 or add amount, parity changes. Track parity to prove impossibility of configuration, tiling, and reachability. Okay, that's the complete concept of chessboard coloring, which we'll be covering comprehensively. But first of all, what are modular invariants? Look at this, modulus, mod 4, mod 8, and mod 3 we have. So we have the positive square residues, which is 0 and 1, and impossible is 2 and 3 because it's completely mod 4 is just squares of 0 and 1 only. And mod 2, this is the most basic invariant, just parity, which we talked before in this. So mod 3 is a digit sum rule. So n, and we have the sum of digits with this mod 9, and mod 9 is nothing but the sum of digits again. So this is the second invariant, and let's go for coloring invariants. This is where things get interesting. Coloring, okay, you take a standard chessboard, you color two similar pieces, then you might be able to find the invariant, but I would prefer the best way is to color a whole column or row, or else you can color four squares or this much squares like that. So first of all, if you color a whole column or a row, you'll lose four white pieces and four black pieces. If you color it with white, you'll gain four white pieces. So the gain and loss is always even. Now this is exactly what the invariant we might need in chessboard cases. And this is actually kind of a popular question. And also if we color four squares with white, we'll lose two blacks and we'll gain two whites, which is still even. So that's the invariant. So can a white or a black piece, like only a single white or a black block, remain? Means no, it can, because we always reduce by even numbers. Now monovariant, it does differ. It's not fixed like invariants, but monovariants are strictly decreasing. It's either strictly decreasing or strictly increasing. So this graph is of a decreasing monovariant. We also have the increasing, but if it decreases, it always increases. If it starts increasing, it continuously increases. It can go increase and decrease, decrease, then again increase like that. So inversion, okay, you have a pair ij, let's say 1 and 2, uh, where I is lesser than j, yes, 1 is lesser than 2, obviously. A1 is greater than A2. Now, this is an out of order pair. We can quite, classify this as an invariant. This is where permutation, parity, and inversions work. Now this is inverted. This is called an inversion because it's completely inverted. I is lesser than j, but ai is greater than aj. So the adjacent swap inversion count by exactly plus or minus one. Parity of inversion flips. That's it. Okay, this is just a standard puzzle. We'll cover it tomorrow in the problem section. So GDC invariance. Now this is a very important concept. GDC is nothing but the greatest common divisor. We have GDC of A and B, and we have uh, A comma B minus A, because this B minus A is nothing but the modular invariance. So you can obviously manipulate it that like that. So we have an example here, 48 and 36. GDC 48, 36 is equal to 38 and 12. I mean 36 and 12. Sorry. So if you see 48 minus 36 is obviously 12. Now this is B minus A, but here A is replaced by B. So this must be denoted as A while you're writing the steps, but you should always consider B. But in the steps, you have to write A because that's the standard exam pattern. Okay, so we can do it even more. If you see, we have this 12 comma 0. You might wonder why is this 0. 12 to 3 is 36, and 12 is completely divisible by 36. I mean, 36 is completely divisible by 12, right? So to b is another as a, and 36 minus n into 12. Uh, so we have graph degree invariant. Okay, now this is kind of simple. You just look at a summation rule. Number of odd degree vertices is always even. That's what we saw in yesterday's problem. Go check it out. The 1 to 4 and minus integers. We have odd numbers, but finally we get the sum as even, and that is exactly our invariance. So there are clean steps to find what is the invariance and find if it's invariance or not. So so these are invariance type problems. So the first type is the impossible configuration. We have show target states that violates the invariant literally. So since the invariant differs from start to goal, goal is unreachable. But it can be done by, I showed you before. Wait a minute. See here, the key inside. We can track parity to reach impossible configurations. So that's not actually quite impossible, but it's quite impossible without invariant. So this is monovariant type problem. Okay, find a quantity that strictly decreases and it's bounded below. Process must terminate in finite steps. It can't quite go to infinite if let's say n tends to infinite. The gap decreases and decreases and decreases until the limits are approximately, I mean, the numbers, like the two quantities, are approximately equal, that the limits are the same. Isn't it interesting? Now we have invariant plus coloring. Reachability characterize all states reachable from a given star by classifying equivalence classes under the invariant. Okay, you just perform some uh, allowed operations so that you can look at what could be reached and what could not. So we have game problems. Identify which player has a winning strategy based on parity coloring or symmetry arguments. That's This is called a game problem because we have many example questions based on games. So here it's just completely parity and coloring. Tiling problems use chessboard or key coloring to show the arguments and color balance conditions. It's not necessary that they will exactly give a chessboard so that we can be able to solve the problem easily. They can't give any other um, cases, but we can literally prove it by taking the example of a chessboard. So let's look at the tech list. Parity, we have mod 2, modulo classes, mod 349, digit sums, divisibility, GDC invariance, prime exponent parities, and we'll look at the geometry processes and combinatoric stuff in the later videos. So we have test coloring and permutation parity already covered, and also the graph degree parity and K coloring. Uh, we just didn't cover weighted sums and inversion count parity of combinatorics in a deep manner. So I'll cover it in a different video. So when you're stuck, you should just test parity and just mod 3 and coloring GDC inversions monovariant. This is a video made for invariant, so I'm not going deep in mod 3, mod 9, mod 4. So you might not be able to understand what it is, but don't worry. When solving tomorrow's problem, you might be able to recognize, and if you're not able to recognize it, when I feel you will not be able to, day after tomorrow will be a video on mod 3, those mod stuff. Like a deep video completely based on this. Okay, we have some elite level IMO tricks. Double invariance, parity plus normal, mod 3. Okay, use two invariants simultaneously when one invariant partitions states insufficiently layers second to achieve a final classification. So we have hidden invariance, weighted rid of unity coloring, potential functions. Okay, these are just basics. We already covered this. You can just ignore these weighted invariants because this is just completely logic. This exact formula can be derived and actually not as taking omega, obviously. According to that question, we can easily derive these. This is the only question you should take care of. So these are just for definitions if you're in high school and attending some exams, writing definitions, conceptual exams. So write what changes. First of all, how to think during a problem, an invariance type problem. Write what changes, and then ask what's unchanged, and you'll be able to decode it from the data on what changes. And then you can just test candidates. If nothing's fixed, you can find direction, and it's not quite an invariance problem, anyways. Try small cases. You can take some example values. Okay. Don't worry if you're thinking that this is just concept. How am I gonna apply this? Tomorrow we're gonna solve super, super, super difficult problems. IMO level problems. 10 problems will solve. Okay. So tomorrow you'll be good with the invariance. Okay, this is the quick formula reference sheet. If you want, you can just take a screenshot of it. I've already explained it, so I'm not doing it again, or the video will be too long. So, okay, final philosophy. Let's end with this quote. Strong students look at what changes. Olympia students first look at what changes, but after that decode what cannot change from it. Whereas Ally students directly invent invariant themselves. We don't have to be Ally students, we just have to be Olympia students. So if you're just a curious student, I'm glad to help you with how to convert and decode these. So that's it for today's video, guys. And stay tuned for the link for the club where we build our future using math, AI, physics, chemistry, and technology. Those are so cool, okay? So tomorrow, make sure to come to this channel so that you'll be able to look at the problems I've solved. So tomorrow you'll be thorough on invariance, even problem solving. So like and subscribe to my channel. Thank you guys. Bye. See you tomorrow.